Alright, this video is a continuation of the comparator series videos, but in this one I'm going to do something a little different. It's not just going to be a continuation of that series of videos. It's going to be kind of a branching off. So this is going to be more of an application of the comparator circuit, not just a simple exploration of it. This series of videos is going to be more about kind of want to go through the entire design process of, I guess it could be a product. I'm not going to do a product. It's not going to be a practical thing. So the idea is really to learn more the process of it. The product is kind of irrelevant, really. Some of it is going to be about the application of the comparator circuit, but I really want to get more into the Simscape model simulation. I'm going to do some more with the multi-domain. We're going to do things with actually building the circuit. We're going to do PCB design with the Simscape environment. I want to get into more the multi-domain. I want to see if I can get into the multibody, which we can actually have our physical system controlling a 3D model. So this project is going to be, I'm going to call it the analog robot. It's going to be a simple thing. It's not really programmable, but it's going to use a series of 4 phototransistors in parallel, and a little motor that will pull a piece of paper. Is going to be kind of like a Scantron, but I'm going to use graph paper, 4 blocks wide and however long. And so if you color in various blocks, it will send commands to an H-bridge motor driver, which will control the direction of the motors. So the idea being that you would write down a pattern of the sequences that you want the robot to go through, and that the robot will drive forward for a certain amount of time, and then turn left, turn right, stop, go backwards. And so you can sort of program a sequence in. It's not actually going to be a true program. It's not really going to be alterable other than just the change of patterns. So that being said, we're going to start off with a component that's quite actually fairly common, called the phototransistor. Now, and if we go into the Simulink model, and we go into the, let's actually just open that up. If we go into open a blank model, create a blank model. And if we open up the library browser and drop down to Simscape, electrical, and if you go to semiconductors and converters, you can see that there's an optocoupler that has a pairing of an LED and a phototransistor, but it doesn't have a phototransistor by itself. But if we go to sensors and transducers, you can see that there does have a photodiode. Now, so there's going to be some difference between the photodiode and the phototransistor. So the phototransistor is basically going to be the same as a transistor, but instead of electrically connecting the base, it's actually activated by amount of light. So it basically works as the more light that shines on the silicon die itself, the more conductive it becomes. So it's a way to control a current through the collector and emitter with the amount of light. So it's a relatively simple device, and if you're familiar with the transistor, it should be pretty straightforward. But, we have a photodiode, so we're going to actually use a photodiode and a transistor to build a phototransistor. Now, there are 2 different types of photodiodes. So here we have, it's basically a tiny little solar panel, and it'll actually generate a current based off of the amount of light. And then we have these other photodiodes that this is more, think of it more as a diode that's reverse biased, and as more light shines on it, it becomes more conductive. So this is the kind of diode that we're actually going to use in the model as well as in the physical build. So these are really common things to be used. I think everybody has a cell phone that will adjust the brightness of the screen based off of the amount of ambient light. So this is basically how that device does that. It uses a phototransistor that detects the visible wavelengths and will adjust itself based off of how bright it is. These are very common in things like motor feedback systems. So you'll have, I'll throw in a picture of one. You have, like, for example, this I think particular motor is from a computer scanner, so a flatbed scanner. And the optical sensor is, you can see it has a little encoder wheel. So it has, on one side it'll have a light emitting diode, usually it's going to be an infrared, and a phototransistor on the other side. So these little wedges, I guess you call it, they're segments along the outer edge of the disk, will actually interrupt in a certain pattern so that the computer monitoring the sensor, monitoring the encoder, will actually be able to figure out it's not only its position over time, like it'll count how many ticks, but it'll also know the direction based off of the position of these two sensors, and it'll also be able to determine, of course, everything from your velocity and acceleration. They're used in lots of other things, but those are fairly the most common ones. So we're going to start off with a simulation. So we're going to just start off with Simscape, or rather Matlab. Then we're going to jump into Simulink. Now I've already opened up a window, so we'll just open that back up. And let's just slide you over a little bit. Now the way that you model a phototransistor is it's actually fairly straightforward. So we're just going to take this photodiode any day now. All right, we're gonna see Control R. Not just kidding. Control R to rotate it. Oops. Control Shift R to rotate it counterclockwise. And yeah, and I want to go to, so I'm in Simscape Electrical. Then we go to Semiconductors. I want a BJT, particularly an NPN transistor. So I'm going to grab this guy. Yeah, throw them there. Now, of course, I'm getting ahead of myself here. So some of them, if you haven't seen the video I did previously on using Simscape, it's the comparator number 2. It's a longer video, but you can kind of skip ahead and jump into the section where I talk about a little more in depth of how to use Simscape to model electrical circuits. But one of the components that we're going to need is this solver configuration. So this is basically, it allows Matlab to actually solve the system. So in Simulink, the various blocks, it'll solve kind of like it'll solve one block and then move on to the next, and then moves on to the next. So it has a unidirectionality to it. Whereas the Simscape models that there's no arrow on these, that's a signal, and that does have directionality. But it's more of a passing energy. So this is much more realistic of a physical system than it is like a mathematical representation, which is kind of more what Simulink is. And so this solver actually allows the Matlab to solve the system of equations simultaneously. So that'd be the most amount of detail. All right, now of course we need a, so I'm actually going to start typing in, so you can just type voltage source, or you can just type voltage, get the second one, DC voltage. I'm going to type in 5 volts. Now I also want an electrical reference. And I know I'm going to need one over here, so we'll just drag that guy over. That's all I did there. All I did there was right click and hold, and just pop it right out. Yeah. All right, so I also am going to, so the transistor is basically amplifying the signal. This is a physical signal input, and so it's going to, I just want to invert that, just because how I want to arrange parts later. So this is basically the input. So you want to, like, you can't really shine a flashlight onto the component like you would a real one. So we need to have a way to basically simulate the amount of light that's falling onto the photodiode. And so this is what this input is. And so we're going to connect up a couple Simulink blocks to it, and we'll basically use a little control knob over off to the side to make myself a little bit more space. And so we'll have a little control knob that, again, will also have a real-time block. I'll just import in a second, and we'll be able to configure. We'll be able to control that in real time and actually see the outputs. So to that effect, I want to import. Let's see. So I'm going to go down to real-time desktop, or desktop real-time, and go down here. I want to real-time sync. And so this is just a, so I'm just bringing in some software. This and a couple other bits and pieces. You have to go back to the comparator number 2 video to see where the process to download the add-on toolbox, and also how to get this. All right, so let's just start connecting things together. And there. So this is going to be my positive VCC, and so the function of the transistor is basically, it's just a simple amplifier. So for an amplifier, I need a resistor. I'm going to use the common collector because I want a positive correlation between the amount of light and the amount of voltage. So I want a emitter, or I want a resistor on the emitter. So just left click and resistor, and Control R. Oh, stop that. 1000 ohms. Control R. Rotate that clockwise. Connect those up. And here, this is the basic model. So here, the amount of light. So as more light shines on this diode, which is in reverse bias, here we have the cathode up to the positive voltage, and the anode going down to the base of this transistor. So the more light that shines on this, or the larger number we put into this signal port, the more this conducts. So the more that this will actually bring this transistor up into saturation. So once we actually have enough current flowing here, so once there's enough light that will allow current to flow through this into the base of the transistor, the closest we'll get to saturation. And you can, we're not going to fiddle around with it too much with the simulation. You can add resistors to the input, like a voltage divider, so you can bias it, and you can control basically where the switching point is. Let's make that a little nicer. All right, so now we need some blocks some Simulink blocks. So I want a control knob, so I'm going to just type in knob. Now for the knob, I can also go up here. I want to do dashboard, and then scroll down and just drag in the knob. And so we also need a constant, and I want that to be 1. Control I to reverse it. I'm going to slide this guy up here, and actually I want to give myself a little bit more space. And I also want another constant. This one I'm going to call 25. I'll tell you why in a second. Now I want a multiplier. Actually, I want a product. Number of inputs. Oops. Control I to invert. And we'll just stick this guy down here. And again, I'm not giving myself enough space. And since this is a Simulink model and this is a Simscape model, you can see the arrows don't match. So if I actually try to connect that, it's not going to let me. So I need a converter. So I want to go from Simulink to physical systems. So Simulink, it already kind of knows what I want. Simulink, and of course it's pointing the wrong direction. Control I to reverse it, or to invert it. And go on, halfway. And now I can actually connect these. So here you can see the arrow is identical, and one is an input, the other is an output. Now I'm going to connect these up. Get out of the way. Jerk. All right, so first we want to connect this to this particular constant. So I'm going to just call this shut up. Okay, it was at this point where only after the fact that I realized that I'm using the OBS Studio to do the video recording, and apparently I set up the hotkey M as the mute my microphone. So good times, learning experience. So I'm going to go kind of try to illustrate what I'm doing. So right here I'm connecting the knob to the constant, and which I'm just calling luminosity. So this is what's actually controlling how much the light is going there. I'm using a second constant and a multiplier kind of as a lazy shortcut. It's just controlling how much light. The knob, I could change it from 0 to 25, but really what I want to do is have just a unit number. So I'm going to build a subsystem out of this, and I want to have a constant that will give me the full range of the diode, so I don't want to saturate it halfway through. As we'll see in a minute in the video, that 25 actually saturates it halfway through. So I changed it back to 13, and yeah, everything works out. I forget what I'm saying at this point. I think I think this is the point where I'm going to start adding in the current sensor and voltage sensor. I want to actually, so this is how you model a phototransistor, but I also want to verify. So anytime you model something, you always need to verify that your model is accurate to what the expectation and ultimately what your real circuit is going to be. So here I'm going over to the Simscape library, going to electrical, then I'm going down to sensors and transducers. So the top there is current sensor. I'm going to measure the current at the base. So this is the amount of current that the photodiode is allowing to conduct as more light comes on. I also want to measure the current through the transistor. I'm also measuring the voltage across the resistor. Yeah, so the voltage sensor, I don't want the wires to cross, so I'm going to hit Control I and invert that. So that just means the wires don't cross. So this current sensor, I'm trying to rotate around because I want again, I don't want the wires to cross. I'm hitting Control R and Control I, some kind of combination. Yep. So here, I'm just going to do the lazy thing and delete the wire. Here, I'm going to just try to do something more clever thing and just move it around, slide that down, and reconnect it. So these sensors operate just like a regular multimeter in real life. So you measure the current passing the signal through the sensor, and voltage you measure across. So we want to make the current sensor the part of the electrical circuit. So we're passing the signal through to the positive and through to the base. And there, voltage also, just like real life, we're measuring across and in reference to one point. So there, I'm just having the electrical reference as the electrical ground is the same reference. Now I'm typing in a scope. I've got three inputs, so I can actually just measure them all directly. But again, here I'm talking about so the Simscape models of the sensors. They have physical signals outputs, and the scope has Simulink signal inputs. So again, we're going to need the physical signal converter. So I'm typing PS, and it kind of anticipates what I want. So I'm going to just drag in 3. Now I'm going to hit Control. Now I'm just going to hit the right-click button and drag, and right-click on the mouse, and so that just reproduces it, connects it to the scopes, and eventually I'll connect. So this will allow me, you can actually see on the converter model. Oh, wait, hold on. So I'm going here, and basically what I'm going to do is I'm going to label the wires so that when I open up the scope, it'll actually tell me which one is which. Because when you open it up, if it's not labeled and one's red, one's blue, the other's yellow, you don't know which one's which. So it's always a good idea to label the wires going into the scope so that you know which one's which. So this is going to be connected to the, that's going to be the load current. That one's going to be the voltage at the output. So that's VO. And this last one is going to be the current at the base of the transistor. So now just all I have to do is connect them so the arrow is matched. So it's a Simulink model. It's a Simscape model to a Simscape converter to convert it to the Simulink model. And I'm just moving wires around. Okay, now I'm talking about that. So the math, the way I have it works out that I've got a 5 volt going in and a 1 kilo ohm resistor. So I'm going to get a 0.5, well, yeah, so 0.5 milliamps, and I want to, eventually I want to multiply that by 1,000. So the voltage is going to be the dominant scale whenever I go to run the simulation. So it's going to be from 0 to 5-ish. And if I actually measure the current in amps, and it's like half a milliamp, it's going to look like a flat line. So basically what I want to do is add in a gain, and to find the gain, it's a Simulink. It's a Simulink model. Here, maybe I'm getting ahead of myself here. Yeah, I think I'm also talking about how the math is going to work out that the current and the current through the transistor and the voltage across the resistor are actually going to work out to be exactly the same, because I've got 0.5, yeah, so 0.0005 amps times 1,000 is going to be the same thing. All right, so now I'm talking about the input at the measuring the base is the transistor is multiplied times 100. So the gain that I'll want at the base of the transistor is going to be 10,000. So if I did 100,000, so it would be 100 times 1,000. Then all three outputs on the scope are going to be exactly the same. So I just went to the Simulink models, added a gain, or maybe I just typed gain and it popped up. So now I realized that it's not just going to let me plop the wire in, so I'm just moving it out of the way, putting the gain back in, reconnecting it. So I want to keep the wire that's labeled on the scope side so that it maintains its label. Now I'm just right clicking and dragging down. This one I'm going to do 10,000. So I want to recognize that the current at the base is going to be 100 times less than the current going through the resistor, because the gain of the transistor is 100. And I'm not actually building a model based off of real values of components. Like, I'm not building a real system. This is just kind of a demonstration of like how it works. All right, so here I want the scope to pop up at simulation. So I click the open at simulation. I'm not going to do any data logging. Actually, I wouldn't. The way I did data logging in the previous video, I would need 3 different scopes. So yeah, that's just a little different. Now I'm resizing it so when I run the simulation, that the scope's not obscured. And looks like I want to do more than 10 seconds. Yeah, 30 seconds. So we get to watch the scope go up and down, lots of wiggly lines for 30 seconds. So click run to do the simulation, and once it's done compiling, I'm going to control the knob, so it's always right at the top. Now I'm going to lower it. And you can see the red lines. I don't have the legend up on the scope. I will, I think, after this demo. But you can see the blue and yellow lines are going to be the voltage and current. I forget which one's which. And the red line is going to be the base current. So you can see the base current is going to be 10 times less than the other two. But the other two are going to be identical to each other. So there's also a little issue came up. So you can it auto scaled at the end of it, but the current at the base, for some reason, it spiked up to 80. And so I'm not 100% sure exactly why that happens. I think it has something to do with how Simulink and Simscape interact. Here I just clicked Tools and inserted a legend, so I know which one's which. Okay, because I wanted to see which one was being a pain in the butt. Okay, so there's I think it doesn't have anything to do with the electrical circuit. I think it has something to do with the order of operations of how something is calculated in Simscape versus Simulink. And I think what I'm going to do here is I'm going to add a delay block. So this will be something from the discrete library in Simulink. Yep, so I'm opening up the library. I'm going to go up to Simulink, discrete. So this is, if you've taken a digital signal processing class, you'll recognize the 1/Z is the delay module. I'm not going to get into all of that. And I think the default is the delay is 1 time unit. And I'm just guessing that that's going to be enough. And of course I realized that I need to back that up because it's a Simulink model. I need to put it in between No, I'm just going to move the wire out. So it needs to be in between the converter, the physical signal to the Simulink converter, just reconnecting it there. Yeah, I think the wire was doubly labeled, so I think I just deleted the label. I just assumed that was going to cause problems. If you have a wire, two wires labeled the same thing, it would probably protest. Yeah, I don't know what I'm saying here. Yeah, it's probably more of the same. Alright, so here I'm going to rerun it. So the scope is still initially going to keep the same scale. So you'll see the traces. They're not as they don't cover up as much of the scope. And also you'll notice that when I get up to about the halfway point, the transistor saturates. It gets to the highest voltage that it will pass. So I'm going to go and alter that in a second. But again, fun wiggly lines. You can see the blue and yellow again are identical. They're right on top of each other because they're both multiplying 0.0005. Yeah, times 1,000. So it rescaled, so that looks like it solved the problem. At the least it gave me the output that I wanted. Whether that is exactly the problem, I don't know. So you can see the current and the voltage of the load. They're identical because it's the same math. It's 1,000 times 0.005. Yeah, it's 5 milliamps, not 0.5 milliamps. Math. Yeah, so here you can see the red line is the base current, and it's 10 times less, but it does track along with the essentially the same waveform. Okay, so now I'm changing it to 13, so that's arbitrarily half because it was about halfway on the knob that it was saturating. Yep, so I'm illustrating halfway. And it looks like I'm running it again. So I'm going to confirm that it looks like it's working. But again, it might rescale. So again, 30 seconds. I don't know if maybe I get impatient and hit pause here or stop the simulation. I don't remember. No, actually, I think I let this one go. But again, it's basically I want a positive correlation. I want the more light that shines on it, the more voltage that that goes to the output. Now, in this circuit that we're going to build, there's many ways that we can actually invert that. If we wanted to respond to more darkness, I would just use maybe that's what I'm talking about here. So if I wanted it to respond to less light, like if the less light that shines on it, the higher the voltage goes, I would just use a common emitter and just put the resistor up at the collector and tie the emitter of the transistor to base or to ground. I think I'm probably just repeating myself here. There's probably just positive correlation. Yeah, I think I'm explaining more the gain, why like that one's 1,000, how the math works out, and yeah. But again, I think I just explained that. Look, waves. Fascinating. I'm not too sure what I'm saying here. I think I'm going to get into just shortly how to actually then so fundamentally what we want to do with this model is to actually build our own component so that we can import it in a later circuit. So I want to build a subsystem. I want to take the basic, just the photodiode and the transistor as a subsystem. Oh, and the obviously the Simulink models as well. So the easy way to do that is you can just make a box around everything that you want. I think that's maybe, I don't think I'm there yet. But anyway, so you can just highlight around all the things that you want. Maybe what I did is maybe I'm just repeating myself because I said actually or too many times, and I'm just going over it because I'm becoming more self-conscious about that. Who knows? So basically what you want to do with the subsystem is that, since Simscape doesn't have an actual phototransistor, what I'm doing at the end of this video is building a phototransistor. So to do that, I want to keep the Simulink models. So here I'm just highlight all what I want. I'm going to have to delete some of it because I don't want the voltage sensor, current sensor to actually be part of it. See, again, I just said actually. So I highlighted it. There's and it puts all in a box, and if you look close, you can see the circuit that you just built. And I think I kind of freaked out about why there's 4 wires and it's not as clean as I wanted. Yeah, so you can click it, expand, and that's basically undo it. And so I'm going to go here. I want to delete what I really don't want. Like I don't like, all these sensors are just to go through the modeling process and to make sure that my circuit's going to work the way I want. So now I don't actually need them. So I'm going through and just deleting the voltage and current sensor. So if you want, you could keep the current sensor and have a 4-part or a 4-component. So if you want to actually measure, so if you want to measure the voltage from the current to the base, you could do that. But essentially, what we just want is a working component. Right now, so also I have to back up here. So what I'm doing is I'm adding a Simulink model. This is going to be an input. So to talk between subsystems, you have to have connectors. So Matlab is smart enough to recognize that the wires going out of the subsystem, it's going to automatically put in the proper Simscape connectors. But I need to change that one constant to a Simulink input. So I really want a component that has just 3 components, and the base, which is just going to be how much light goes into it, is going to be a Simulink input. And so then I'll need to add a constant outside of that outside of the subsystem, so that the knob will still be able to reconnect it in the same exact way. So here I'm learning that, oh look, I can actually just get rid of that highlighted box, and I think I was just trying to figure out if there's a way to completely undo it, and apparently there is. But I'm just going to highlight it again anyway, and then I'm going to hit right click. So these are all the components that I want inside my subsystem, and it's just a nice way to clean things up. And I'll show you in a minute, or just a little bit, how you can actually make the component and save it in an external library and import it again whenever you want. So here I am deleting that, and I want my model to look physically like a NPN phototransistor. Here I'm just going through. Yeah, there's too long of a title. I'm going to type emitter and collector, or collector then emitter, and later on when I'm editing the library, I'm going to change that to E and C, because everybody who works with the transistor probably is familiar with the difference between the emitter and collector. So we actually have we have 3 connectors. We have 2 Simscape connectors and 1 Simulink. And I think I'm just calling this, I don't know, I can't see it right here. It's probably Luminosity. Again, if I hit N, or if I typed M, it would also again mute my microphone, and I wouldn't have to go back and do a voiceover. But hey. So you can move the connectors around on your model. So I want it to look much more like an actual transistor schematic. So we've got the collector at the top, the emitter at the bottom, and then the base at the left of the model. And I'm resizing it I'm basically just making my own electrical component. So you can see in the box subsystem, it's a Simulink input arrow. Yeah, I'm just getting rid of a bunch of other stuff that I don't need. We've already modeled all the other values, so I'm just getting rid of that stuff. All I'm looking to measure at this point is the output. I'm just kind of cleaning things up, moving things around, and so here, let's see, what am I doing there? I don't know what I was doing there. Maybe I'm talking about, like, you can add an additional inputs and outputs if you want to measure the internal performance of your system as you're connected to your larger system. I don't know. All right, now here's where I'm basically rebuilding the system. I want to have the same output, so I'm putting in another constant, and again, this will just allow me to have the input go from 0 to 1. Since it's a Simulink input, I can connect the Simulink constant and directly going through the same process. I want to select the constant, check it, and my input's from 0 to 1. Click OK. And so this should be, now I'm just going to continue cleaning it up. So it looks basically, your traditional transistor. as your input. We should get the same exact output voltage that we were before. I think here I'm just kind of straightening things up. No, I'm going through. That's right. I'm changing the scope inputs from 3 to 1 since we obviously only have 1, and it didn't pick the right one to keep, so I've got to reconnect the wire. Now it's fighting me. It's being a pain. Come on, work with me. There we go. And keep the label. So this should function exactly like before, obviously minus the 2 other measurements. We're only measuring the output voltage, and we're keeping the same resistor value, so we can assume that the voltage output, or the current through the resistor, is going to be the same if the voltage output is the same. So I'm going to click run. Again, this is going to be 30 seconds of squiggly lines, and I forgot to resize that window so we don't get to see the first, what's that, 5-6 seconds of the simulation. So now, controlling the knob. I think if I used a slider, I might get a little better fidelity. You can see as I'm moving it around, sometimes it wiggles on me, just like right there. But anyway, so this is just testing that our subsystem works and that our simplified and I would say much more cleaned up version is continuing to work the way we want, so we can move on to bigger and brighter things. Yep, I'm pointing to squiggly lines, so that's our voltage output. That's still a positive correlation between the amount of light in. So here I want to actually, here I want to copy it. No, actually I meant to cut it, because I want to save this into a library. So once you start making your own circuits, your own subsystems, you can build your own library. There's also a way you can make this appear in the library browser. There's on Matlab's, or rather MathWorks website, you can do that. So here I'm creating, I just went back to the Matlab library, Simulink, and created a new library, pasting the component in. I'm not too happy with the amount of words and letters that's on there. I also want to import a photo. I want to basically make a schematic symbol that is a functioning component. But anyway, so this you can build up a series of parts and subsystems. Okay, so here I want to add an icon, so I'm going to a mask. So the mask is something you put over it, just like a mask. And this is just something I shamelessly stole from the internet, so if you recognize this is yours, sorry. So yeah, I'm just going to browse to the image that I shamelessly downloaded off the internet. Maybe it falls under fair rights. I'm not doing this professionally or anything. So there's different options. You can choose to have opaque, so all you see is the photo. You don't see any of the circuit or any of the labels. I'm going to choose to do opaque with ports, so you can see it. But now it's here. I need to resize it because I want it to look a little bit more realistic. That looked distorted, and so you can double click on the model, and I'm going to go back and edit the port labels. So this one I'm just going to keep E for emitter. The other one I'm going to change for C for collector. What I really should do is also shorten up those ports and just bring them a little closer, and there's no need to have them sticking out so far. And I think I just shortened up the base input. I don't know what to just call that, loom. So again, I would have muted it. Anyway, so I unfortunately the ports don't line up directly with the lines of the schematic, but beggars can't be choosers. There might be a way that you can force Matlab to do that, but I didn't figure it out. Now, basically what I'm going to do is import this back in from the library. It's going to yell at me because I haven't saved it yet. And of course it doesn't line up just so we're just having to do it manually. Oops. Now I have to save the library before it allows me to import it. And so this is I'm saving the library. So you can add other subsystems into this library, other parts, other circuits that you build, especially if there's something you want to reuse or you can reuse. For example, I'm making my own electronic component. This is definitely something I want to reuse. So I'm building up a library that I can then reference to later. So I'm pretty happy with this. And I think pretty shortly I'm going to be just hopping into the actual physical build. No, got to run it one more time, just in case adding a picture and relabeling the ports screws things up. Now you never know. I hit M and muted the microphone, so it's always good to check. Yeah, that's where I say, all right, mercifully, we're not going to wait another 30 seconds. All right, so I think the rest is, so this is how you basically build your own electronic component and model it in Simscape. Let's go to the real world circuit. How about now? Now? Any second. Wait for it. Alright, so I've got two different circuits hooked up. It's here on the left, I've got the photodiode and a transistor and a current limiting resistor. And on the right, I've got a actual phototransistor, which is the same current limiting resistor. I'm using the same value just so I can get comparable readings. So, as you'll see on the oscilloscope in just a second, what I do is I'll wave my hand over like this and block some of the light, and you'll actually see the results in the oscilloscope. Alright, so channel 1, the yellow channel, is the photodiode and transistor, and channel 2, the blue channel, is the phototransistor. So here I am waving my hand over, see if I can do it consistently. You can see the phototransistor is pretty responsive. So you have to cover over the photodiode quite a bit more before it actually drops down. So I got my hands cupped over it pretty well, and it's obviously not going to block all the light. But you can see it takes a bit more for it to respond. But also, if I move the light source closer, you can see the phototransistor actually responds a bit more and actually will increase in output. So it's going to max out at 5 volts. So we're almost there. So now this is just a simple NPN transistor. This is the N2222. So if we want to get a more response, we amplify it a little bit more. So I need a little bit more gain. So I'm going to swap out the 2222 for this tip 122 transistor. And of course, I turn the power off first. And of course, the NPN, the 2222, is going to be emitter base collector. Now, they just have to be different. It's got to be base collector emitter. So, turn the power back on. Now we'll be able to see that the photodiode with the Darlington transistor is actually quite nicely responsive. Again, the yellow channel is the photodiode with the Darlington transistor, and the blue channel is the phototransistor. So let's see if I can do this evenly. Well, almost. So you can see the increased gain of the Darlington transistor actually increases the, or should I say, it narrows the bandwidth of response. So it's only a relatively small change in light, which it actually saturates. It goes from fully on to fully off. I can actually just wave a couple fingers over it. I can just wave my hand over it and get this kind of fun response. Now I can also add a DC biasing voltage to the base to get it to the switching characteristics that I want. Now here I've added a potentiometer. The idea is that I want to add a DC bias voltage to the base of the transistor. So this is the same base that the photodiode is connected to. The idea is that I can change the characteristics, so I can either lower the output voltage or raise it. So this isn't going to change the amplification, but it's just going to set the voltage level a little bit higher or lower. So I can change this, so I can set this photodiode and Darlington transistor combination to operate a little more closely to the phototransistor. So if I actually take this little piece of wood, you can see I can control the amount of light that each of the sensors sees. Now if I move it slowly, you can see the phototransistor responds a little more slowly. That has to do with the gain. So the yellow one is the photodiode, the transistor, and the blue channel is the phototransistor. You can see the output level is about the same. Now if I actually move the light source, if I move it up, you can see they respond a little bit differently. So I'll move it back down, see if I can get it right about the same height. Silly light. Now if I wave this piece of wood back and forth really fast, you can see it actually responds at this particular light level very similarly.